I'm analyzing a Perceptron model's performance. A perceptron is a simple type of machine learning model, kinda like a basic building block for more complex models. We're looking at how well it predicts outcomes based on input data. We trained the perceptron on a dataset and achieved 95% accuracy, which is pretty good. However, when we tested it on a completely separate dataset, the accuracy dropped significantly to 70%. That big difference is what we need to investigate. This is the most likely problem. It means the model memorized the training data too well, including any errors or quirks. It's like a student who crammed for a test and aced it, but forgot everything afterwards. The model performs well on the training data, but poorly on new, unseen data. This is unlikely given the high training accuracy. If the model was underfitting, it would perform poorly on both the training and test sets. It's like the student who didn't study enough and failed both the practice tests and the real exam. This is possible if one type of data, a class, is much more prevalent in the training set than the test set. The model's performance can be misleading. It might get really good at predicting the majority class, but struggle with the minority class in the test set. This is like a teacher focusing only on the top students during the year, and ignoring everyone else. The end-of-year results will be very biased. A high learning rate can be a problem. Think of the learning rate as how much the model adjusts its internal settings with each piece of training data. A high learning rate can cause the model to overshoot the best settings, missing the optimal point and leading to poor generalization. It's like a person trying to find a specific point on a map, but taking huge steps every time. They may overshoot it. I see a high training accuracy and a low testing accuracy. That screams overfitting. The model learned the training data too well, including its quirks and noise. It's like a student who memorizes the textbook perfectly but can't apply that knowledge to new problems. Maybe the dataset has a lopsided class distribution. Imagine more examples of one type of flower than another. The model could be great at recognizing the abundant flower, but it stumbles on the rare ones, especially in a test set with different proportions. That's a classic case of misleading accuracy. A high learning rate is like taking huge steps while climbing a hill. You might overshoot the summit and never find the best spot. That's what happened here. The model jumped around in its search for the best solution, leading to poor generalization. I see a big difference between the model's performance on training data, 95% accuracy, and testing data, 70% accuracy. This tells me something's wrong with how well the model generalizes to new, unseen data. It's like a student who aces the practice test but bombs the real exam. We need to figure out why. This is a strong possibility. The model learned the training data too well, picking up on random quirks and noise, instead of learning the underlying patterns. Think of it like memorizing the answers to a practice test instead of understanding the material. That's why it does well on the training data but fails on the test data. The problem is this huge gap between the model's accuracy on the training data, 95%, and its accuracy on the testing data, 70%. This is a classic sign that something is not right, and it's likely related to how well the model generalizes to new data. My goal is to understand the cause of this. A high learning rate means the model's adjustments are too big. The model might jump over the best solution, never finding the ideal settings. It's like trying to find your way through a maze by taking giant steps. You could miss the correct path entirely. This can lead to poor generalization because the model never settled into a good spot. This is less likely because the model performed well on the training data. Underfitting happens when the model is too simple to capture the data's patterns. In this case, if the model were underfitting, it would have performed poorly on both training and testing data. It's like trying to build a complex house with only Lego blocks. The house isn't complex enough and won't fit well to the real world. This is also a possibility. Maybe one type of data point is far more common in the training set than the other. The model could have learned to predict the majority class very well but struggles with the minority class. The test set may have a different balance of classes, leading to the drop in accuracy. It's like learning to identify cats and dogs only from pictures with 90% cats, then testing on an even split. You'll be amazing at cats but terrible at dogs. I see a high training accuracy, which makes underfitting unlikely. Underfitting means the model is too simple to capture the data's patterns, resulting in poor performance on both training and test data. That's not what we see here. We have a great training score. This is a strong possibility. A large difference between training accuracy, 95%, and test accuracy, 70%, is a classic sign of overfitting. The model learned the training data too well, including its noise, and can't generalize to new data. The model memorized the training data. A high learning rate can cause the model to overshoot the optimal solution. Imagine you're trying to find the bottom of a valley. A high learning rate might make you jump over it and never settle down. That prevents the model from learning properly and can also lead to poor generalization. This is a more subtle possibility. If one class in the dataset is much more common than the others, the model might perform well on the training set but poorly on the test set if the class distribution is different. It's a bit sneaky. Think about having more examples of cats than dogs in training. The model might become biased towards cats. This is the core issue. The model performs extremely well on the data it's already seen, training, but much less well on new, unseen data, testing. This discrepancy hints at a problem with generalization, the ability of a model to perform well on unseen data. This is the big picture. We are examining the performance of a perceptron, a simple type of neural network model using metrics like training and test accuracy. I see a big difference between how well the perceptron model performed during training, 95% accuracy, and how well it performed on new, unseen data, 70% accuracy. This gap suggests a problem with the model's ability to generalize to new data. This means that during training, the model correctly classified 95% of the examples in the training dataset. It learned the patterns in that specific data very well. However, when I tested the model on a completely separate dataset, the test set, its accuracy dropped to only 70%. This highlights a significant problem with the model's ability to generalize. The large difference between the training accuracy, 95%, and the test accuracy, 70%, is a major red flag. It tells me that something is wrong with how the model is learning. Several things could be causing this. I'll investigate a high learning rate, overfitting, and class imbalance as possible explanations for the poor generalization. A learning rate that's too high could cause the model to jump around too much during training, missing the best solution and therefore failing to generalize well to new data. Think of it like trying to find the bottom of a valley. A high learning rate is like taking giant leaps, potentially overshooting the bottom and never finding it. Overfitting happens when the model learns the training data too well, including its noise and quirks. As a result, it performs well on the training data but poorly on new, unseen data. This is a very common problem, especially with more complex models. It's like memorizing the answers to a test instead of actually understanding the material. You'll do well on that specific test, but you won't be able to answer similar questions. If one class in the dataset is far more frequent than another, the model might be biased towards the majority class, leading to good performance on the training set but poor performance on the test set, especially if the test set has a different class distribution. It's like training a dog to recognize cats and only showing it pictures of cats. It'll be great at recognizing cats, but might not recognize dogs as well. I'm looking at a discrepancy in the performance of a perceptron model, a simple linear classifier. The model shows high accuracy on the training data but significantly lower accuracy on unseen test data. This is a key concept to understand in machine learning. This is unlikely given the high training accuracy, 95%. If the perceptron were underfitting, it wouldn't be able to capture the patterns in the training data, so its performance would be poor on both the training and test datasets. Think of it like trying to fit a small square peg into a large round hole. It just won't work. This is a strong possibility. A high training accuracy, 95%, and a significantly lower test accuracy, 70%, is a classic sign of overfitting. The model has essentially memorized the training data, including its noise. Thus, it performs poorly on new, unseen data. It's like cramming for a test. You may ace the test itself, but you won't retain much information. This is also plausible. If one class in the dataset is significantly larger than the other, the perceptron might be highly accurate for the majority class but perform poorly on the minority class. Because the test and training datasets might have different class distributions, This could result in a large performance difference. Imagine a dataset with 90% of data points belonging to one class and 10% to the other. A model that only predicts the most common class can still have high training accuracy but poor generalization. High learning rate means the model is making big adjustments in its parameters at each step during training. This can cause it to overshoot the optimal weight values, missing the sweet spot of best performance. Like taking huge steps when trying to cross a narrow plank. You're more likely to miss your target and fall off than if you took small, precise steps. This is less probable compared to other options but possible. It can lead to poor generalization, resulting in the performance gap observed.